Okay, we are going to officially start our session this afternoon. This is our first session. So good afternoon, everybody who joined us. Thank you for joining us in our session. My name is Helen Chan, and I will be your moderator this afternoon, along with Joe Packham and Mark Goldstein, who will join us later on this afternoon. For the next 30 minutes, we'll be reviewing lesson 24.1 on Pythagorean theorem from the Introduction to Algebra program. We'll be presenting a series of 3 live sessions this afternoon. You can see from the schedule that each session is approximately 30 minutes long with a 15-minute break in between. We hope that you can join us for all 3 sessions, but if you are unable to, these will all be recorded so that you can watch the sessions at a later time that is convenient for you. All you have to do is to go to the e-learning page on our website using the link that Joe emailed you and click on the watch session button of the session that you want to access. Okay? If you are watching this as a pre-recorded session and need to contact us for any assistance, please feel free to email one of us and we'll be happy to answer your questions. If you missed jotting down our email address for this right now, don't worry, we'll put up our contact information later on at the end of the session. Okay? All right, so I'm going to go back to the warm-up slide. So the warm-up for this session was, I just wanted to get a little bit of feel for what you remember about right triangles, and I try to get the session started by putting some attributes myself, but then I see that many of you also joined in and wrote some of these facts that you know about right triangles. Okay, so first of all, we know that there's one 90-degree angle, and that 90-degree angle is actually opposite the longest side, and that longest side is called a hypotenuse. Someone else wrote that the sum of the square of the 2 legs equals the hypotenuse squared. Okay, that's actually one of the things that we will explore this afternoon, so I'm glad that somebody brought it up. The sum of all angles is 180 degrees. That's actually true of all triangles, so it's certainly true for right triangles as well. The square of the hypotenuse minus the square of one leg equals the other leg squared. Okay, yeah. Again, we will explore that as well. Any other ones that you would like to add to this list? Or should we go on? Oh, I see that somebody else has joined us. Hello, Tony. Welcome to our session this afternoon. Okay. Do you have any questions about any of these attributes? Are these accurate? Would you disagree with any of these statements that have been put on the whiteboard? Or are we ready to move on? No questions? Okay. Then why don't we move on? Okay. So here are the goals for lesson 24.1. This lesson comes near the end of the geometry cluster in the Introduction to Algebra program. In earlier weeks, students have derived formulas for areas of triangles and parallelograms using what's called dissection proofs. And also the squares and squares roots lesson, which I did the last time we had a live session, also comes before the Pythagorean theorem lesson. Throughout this lesson, we'll also see elements of the fourfold way, which is representing solutions numerically, algebraically, geometrically, and verbally. Okay. Okay. So this is from SP2 in week 24. Here's a right triangle in blue. Okay. And we are going to define the distance, okay, between two horizontally or vertically adjacent dots, okay, as one unit of length. So right here, let me get my little pointer. Wait a minute, I'll get my finger. Okay, thank you, Joe, for doing that. But yeah, so this is considered 1 unit length going down, up and down like this, or across also from dot to dot, okay? So if we define that as 1 unit of length, then if we draw a square using that measure, then we get 1 square unit, okay? So now we're going to look at the right triangle, okay? And what is the shorter measure of the shorter leg? You can type your answer in the chat box, okay? Again, the question is, what is the measure of the shorter leg on this right triangle? Okay. Okay, Connie says 3, Pat says 3, okay, good. What is the measure of the longer leg? Okay. 4, good, okay. Now, Joe, what I'm going to ask you to do is to draw a square on the shorter leg right here, okay. And I would like to ask everyone to type in the chat box the area of the square that Joe just sketched, okay. Okay, and that's in square units. Okay, okay, Joe, if you would do the same thing to draw a square on the longer leg. And again, everybody type in the chat box the area of the square on the longer leg. Okay, so far I think everybody agrees, okay, 9 square units and 16 square units on each one of those. Okay, now if we look at, okay, the length of the shorter leg and the area of the shorter leg, okay, and if we also look at the length of the longer leg and the area of the square on that longer leg, okay, do we see any relationship? You can go ahead and type that in the chat box as well. Okay, so Joe probably or whoever tie these two measurements in. So what is the relationship? Everybody's eagerly typing. That's great in the chat box. So what is the connection between the length? Okay, all right. Connie says that the length of the leg squared, okay, is the area. Pat says 3 squared and 4 squared is the area. Okay, click on the happy face if you agree and you understand so far. Okay, great. Okay, so now let's draw a square on the hypotenuse. Joe, I'm going to let you handle that. Okay. And I want everybody to think, okay, keeping in mind how you may have done the dissection lesson already, so that might give you a hint, but how do we determine the area of the square that Joe just drew? Okay. How can we determine the area of this square? I'm just waiting for the chat box to see your responses. Okay, and if you already have an idea, okay, if you have an idea, you can go ahead and do this on your student pages, and then you can type in the answer in the chat box for us. Okay, so Connie says, Jill says, break it up into smaller pieces and shapes, and we can determine the area, okay, probably of the whole thing, right? Connie says, I can find partial areas of the square, okay. Pat says, count the squares, okay. Those are good ideas. Does anybody actually want to do it for us? how would you actually break it up? Okay, Joe wants to do it. Okay, thank you, Joe. Okay. All right, so one way to do this is, if you can see what Joe has done here, she's basically broken up this square, okay, into 4 congruent triangles with a little extra square in the middle. Okay, these are 4 exactly, Connie. These are all 4 right triangles. So that was nice of me. So if we know the area of a triangle, okay, we can multiply that 4 times. So let's see. This is a triangle, right triangle, with a base of 3 units and a height of 1, 2, 3, 4. So half of that would be half of 12, which is 6. And then if you multiply it by 4, 6 times 4 will give us 24. And then don't forget the square in the middle. So that makes it 25 square units. Okay, did we follow that? The other way that we can do this, okay, is that I'm going to attempt to do this. And let's try to use a different color so we can see it. The other way that you can do this is that you can draw sort of another figure, a rectangle, I think. Let's see. Okay, so if you enclose this and you kind of, if you do it that way. Now, we don't have to actually figure it out, but I'll just explain to you what we're going to do. What you could do is you can figure out the area of this red rectangle here, and then you can subtract out the pieces that are actually not part of the square that we're trying to determine the area of, and that'll get you what's left over. Then is what's inside. Does that make sense? Click on the happy face if that makes sense to you. Okay. All right. Okay. And then how do we find the length of the hypotenuse if we know that the area of the square on the hypotenuse is 25 square units? And that's part of the reason why I asked you about the relationship between the length of the leg and the area of the square on the leg. So if we know that same relationship, how can we figure out the length of the hypotenuse? Well, what is the length of the hypotenuse then, if the area is 25 square units? Okay, thank you, Tony. It's 5 units. Okay. All right. Okay. Let's do this one real quick. So, Connie, if you would please draw, okay, the square on the shorter leg, and find out the length and the area. Okay, so basically, if you can fill out this, the first line and the third line in this table, okay. If I can have Pat, okay, do the length of the longer leg as well as the area of the square on the longer leg, okay. And then let me have Joe. Tony, I'll call you on the next one, okay. Joe, if you could do the area of the square on the hypotenuse and the length of the hypotenuse. And thank you for the color coding, Joe. Okay. I'm going to set the timer for 1 minute. Let's see if this works. Okay. All right. Okay, and Pat, if you are finished with your assigned part, you can go ahead and type in your answers onto this table. Just remember to use the A without the box around it. Okay, and Jill is finishing up the area of the square and the hypotenuse. So far she has that it's an 11 by 11 square for the red square. Okay, and once we figure out the area of one of these right triangles, okay, so she figured out. So she's going to take out 56 square units because the area of one of the triangles is, let's see, 14 and then times 4. Okay, and whatever 121 minus 56 turns out to be, which I believe is 65. That's the area of the square on the hypotenuse. And so to determine the length of the hypotenuse is the square root of 65 units. And that turns out to be a radical, and it's okay. We'll just leave it like that for now. Okay. All right. So now, what I've done actually while I was preparing ahead of time is I had combined the information that we recorded from the previous 2 slides. And if you look at the highlighted rows from each column, okay, you can see a relationship between the areas of the squares on the legs and the area of the square on the hypotenuse. So if we're looking at this number, the 9 and the 16, and the 25, and then the 16, the 49, and the 65. Okay, we're going to write a conjecture, okay, about the relationship between these 3 numbers. So what can we write? What observations can we make about these 3 numbers? These groups, each of these 2 groups of 3 numbers here. Anyone? So again, the question is, what is the relationship between these 3 numbers in the smaller triangle and in the larger triangle that we collected? Okay. Jill says if you add the squares of the legs, so that would be like 9 and 16, or the 16 and the 49, then you get the square off the hypotenuse. Well, let's see if that's true. If you add the 9 plus the 16, do you get 25? You do. And if you add the 16 plus the 49, do you get 65? And indeed you do. Okay, Connie says the area of the shorter leg plus the area of the longer leg is equal to the area of the square on the hypotenuse. Okay, so it's pretty much the same thing that we've been talking about. So that's what the conjecture is right now. Okay, but this is just based on 2 examples that we just did. Okay, so we want to know, how can we show that relationship we observed is always true? Okay, that this relationship is going to hold true no matter which triangles we try this on. Okay, and so that's what that's really the main part of this lesson. Okay, now here are two squares. Okay, the blue one and this yellow one, and they were constructed using this using the side lengths from this right triangle right here below. Okay, and so what I want you to do now, okay, is go ahead and Joe, would you please label the sides, okay, on the blue square based on this triangle right here, okay, and Pat, would you please find the areas of each of these sections, okay, based on the dimensions that Joe provides. Connie, would you please label the sides on this yellow square? And Tony, would you, based on the measurements that Connie gives you, would you write the areas of each of these pieces inside for me? Okay, and I'm going to set the timer for 1 minute, and let's try to do that within 1 minute if we can. Okay. So Pat and Tony, you are writing the areas on the inside of each of these pieces, okay? And while you guys are doing that, I'll just ask you, do you think these two squares are congruent? Happy face if you think they are. Sad face if you think they're not. Okay. Connie says yes. Okay. Connie, can you tell us why you think that these two squares are congruent? Based on what observation that we have here, do you think that these two squares are congruent? Okay, yeah, because you see that the side length for both of these squares is A plus B, right? Here you have a combination of B and A, and over here you have B and A. So they both have the same dimensions, and therefore we know, even though maybe the parts inside are not the same, that's because the dimensions are the same. We know that they are congruent. Okay. All right. So let's see if we can move on. Okay. So these are. Will I change the area of these two larger squares if I just cut them apart, but still keep them together? Does cutting them apart change? Okay, no, that's correct. Okay. Okay, and we can write so if we wanted to figure out the area of the larger square, okay, all we have to do is add up the partial areas here. So for the blue one, we would have a squared, okay, plus AB, plus another AB, plus B squared. Or if we wanted to simplify that, we can write A squared plus 2 ABs, and then B squared. Okay, and similarly, if we wanted to write determine the area of the yellow square, that would be 1/2 AB plus 1/2 AB plus 1/2 AB plus 1/2 AB plus C squared. Okay, and we can simplify that too. Okay, all right. I'm going to move on to the next page. Okay. So now, how about this? What if I rearrange the pieces? Will that change the area? Nope. Okay, that is correct. We won't change the area just because we are rearranging the pieces. But what I've done here is I pretended that I cut the pieces apart and I rearranged them. And now you can see that if I combine two of the right triangles, the yellow right triangles, that actually equals one of the AB rectangles, okay, one of the blue rectangles, okay, and we have two sets of those, okay. So what we can write here, okay, is once I cross these out, and I'm going to cross them out, Joe, okay. If I cross these sides out and these sides out, would you type in the chat box, what is the simplified equation that I can write? Based on what we have left. So what do we have on the left side of the equation? What do we have on the right side of the equation? Okay. Yeah. So now we have, and I'll type it here. I'll try to type it. So we have A squared plus B squared equals C squared. And that is the relationship that we have. Okay. So now I'm going to move on to the next page so you can see. So now remember, these are the leftover pieces. I had an A square piece, a B square piece, and a C square piece. Now I go back to the triangle that I had, And I put the pieces that were left along each of the sides of this triangle. And so now we can see, okay, that, for this right triangle with legs A and B and a hypotenuse of length C, okay, the sum of the squares of the length of the legs is equal to the square of the length of the hypotenuse. So this relationship is what we call the Pythagorean theorem. And we have just used geometry and algebra to verify that the conjecture we made earlier is true. Okay? And when a conjecture is true, it's called a theorem. Okay? Once we prove it for all cases, then it becomes a theorem. It's no longer just based on a couple of numerical examples. Okay? So that's what the Pythagorean theorem is. Okay? Click on happy face if you understand what I said. Okay, thank you for the affirmation. Okay, so here's a math background taken from the teacher pages. And I just want to highlight a caution with the slogan of the Pythagorean theorem. We are all familiar with the slogan A squared plus B squared equals C squared. And it's very catchy and easy to remember. But it's actually an incomplete statement of the actual theorem because there's no reference to a right triangle or and it doesn't tell me which of the sides, A or B or C are the length of the legs or the hypotenuse. So what this math background does is that it gives you 3 alternative ways of stating the theorem. And so just please take the time to review them before you teach a lesson to your students. Okay. There's another, in the teacher pages, also an error alert on combining like terms. When you have to do that geometric proof, there was a lot of combining like terms like 1/2 AB plus 1/2 AB and so on. And this page just kind of alerts you that, the students often make errors when combining like terms, especially when it involves like fractional terms. The student warm-up for this lesson, which I didn't go over in this session, includes some practice on combining like terms. Okay? And the lesson 24.1 ends with some practice on the converse of the Pythagorean theorem, which I've highlighted here in red. Oops, sorry. Oops, it didn't make it through. Oh, well, I would just talk about it. Is that there's also something called the converse of the Pythagorean theorem, which says that if you know that the sum of the squares of the length of the 2 shorter sides is equal to the square of the length of the hypotenuse, then the triangle that you have is a right triangle. Okay. So for example, on this white page, I'll just type in some numbers for you to try. Okay. So let's suppose I have a triangle with lengths 4, 5, and 9. Okay. So go ahead and Connie, can you go ahead and determine if these 3 sides, these side lengths, belong to a right triangle? Okay. And I'll have Joe, would you do, actually let me have Pat do it. Okay, 5, 12, and 13. Okay. So Pat, I want you to determine if those 3 sides are the side lengths of a right triangle. Okay. And Tony, if you would please do 6, 8, and 10. Determine if those 3 belong to a right triangle. And Joe, you will do 5, 6, and 11. Okay. So you each have your workspace there, and I'll set the timer for 1 minute real quick. Okay. All right, so Connie determined that hers were not the length of a right triangle because 16 plus 25 does not equal 81. Okay, and Joe is doing trying to determine if 25 plus 36 equals 121. Okay. Okay. All right, so I put some red dots next to the ones that were right triangles. Okay. If you didn't get a red dot, that means yours was not a right triangle. Okay. There's one thing in on SP7, problem number 4. It talks about Pythagorean triples. It's just kind of piggybacking on this, whole Pythagorean theorem thing. Pythagorean triples basically just means that all 3 sides of the right triangle are positive integers. So looking at the 2 triangles that do qualify as right triangles, are any of these Pythagorean triples? Yes, no. Okay, are they integer, are they positive integer dimensions? Okay, if they are, and they actually are here, I picked out some nice and funny numbers for you, but yeah, both of these examples were indeed Pythagorean triples. Do you know any other Pythagorean triples? If you do, go ahead and type them in the chat box. Like I can tell you one of them is, I'll type one in, 3, 4, Connie beat me to it, 3, 4, 5, 6, 8, 10 was one of them. I think 12, 16, 20 is one of them also. Okay, and 8, 15, 17 is also one of them. Okay, and there's many other ones. Just as long as you have three numbers that are positive integers, and they meet, they do meet the qualification of a right triangle. Okay. Do you have any questions on this page? We kind of ran out of time, so we kind of want to wrap things up now. Any questions? No? Okay. All right. Well, thank you very much for joining us for this session. That's the end of the Pythagorean theorem session. And if you like to participate, and I hope you do, and like to participate in the next session, it starts at 3:45, but you can actually sign in now. You just have to make sure that you log out of this session before you go to the next session, and just click on session 20. Okay, and thank you very much, and I'm going to go ahead and stop recording now.